Netherlands built a defensive shield against the massive ocean that is so impossibly large it completely defies conventional engineering logic. 13 gigantic storm surge barriers, 29,000 kilometers of reinforced levees, over $7 billion in cost. That is a defensive line long enough to stretch more than halfway around the entire Earth, placed directly into the violent North Sea. One winter night changed everything. 1,836 people never saw the next morning. Now watch what they actually built to push back the ocean. Every meter was fought for. No shortcuts. Status update required immediately. The storm is intensifying.
Confirmation requested on barrier integrity systems.
Half the country disappears underwater in hours. So how did this nightmare force them to build it? January 31, 53. A massive hurricane-force storm builds over the icy North Sea, heading straight for the low-lying Dutch coast. A high spring tide combines with the extreme storm surge. The wind pushes millions of tons of water against the fragile coastline. Centuries-old earthen dikes are forced to face a hydrostatic pressure they were never designed to hold back. 89 different dikes breach almost simultaneously. Millions of gallons of freezing salt water rush inland at a terrifying speed. Whole rural villages are swallowed up to their brick roofs. The angry sea reclaims over 1,300 square kilometers of land. The nation realized they could not just repair the old dikes. They had to close off the sea. But there was one massive problem. Massive problem? The country's economy relies on these open waterways. You cannot permanently block the port of Rotterdam, the busiest in Europe. And worse, there is no solid bedrock. The entire seabed is made of shifting sand and soft clay. It is basically underwater quicksand. In 1854, the government made a radical choice. They would not just build higher walls, they would mathematically shorten the coastline. By damming the major estuaries, they could reduce the vulnerable coast by 700 kilometers. This was the birth of the Delta Works. But then, a new crisis emerged. Closing off the eastern Scheldt meant killing a unique, incredibly valuable saltwater ecosystem. The fishing industry would be wiped out. The environmental cost was too high. So, the government ordered a complete halt. Halfway through construction, engineers were forced to throw away their blueprints. They had to design something that had never existed. A storm surge barrier that remains open to let the tides flow, but can snap shut the moment a hurricane approaches. This meant placing gigantic movable steel gates right in the middle of a deep, violent ocean channel. The hydrostatic pressure on a closed gate would be immense, equivalent to the weight of 12,000 cars pushing against one joint. To hold that back, they needed concrete pillars the size of cathedrals, weighing up to 18,000 tons each. These giants had to be perfectly placed in 45 meters of churning water. 1 centimeter of error meant absolute structural failure. And they still had not solved the biggest problem. How do you anchor 18,000 tons of concrete onto shifting underwater quicksand? Drop 18,000 tons of concrete on wet sand, and the ocean currents will immediately wash the sand out from underneath. It is called scouring. The massive structure would simply tilt, crack, and collapse into the sea within months. They could not pour standard foundations. The water moved too fast. They needed a completely new way to stabilize the seabed. Engineers built massive physical scale models in specialized testing facilities, blasting them with artificial waves to test a radical new idea. If they could not reach solid bedrock, they would simply have to manufacture their own bedrock, layer by layer. The solution was a colossal foundation mattress, a multi-layered high-tech carpet made of synthetic fabric, sand, and heavy gravel. That is roughly the size of 2 professional football fields. and they needed to construct exactly 65 of them. The layers acted as a mechanical filter. They allowed seawater to flow through, but trapped the fine sand underneath. When placed on the ocean floor, this flexible armor would lock the liquid-like quicksand in place forever. But having the perfect design on paper was one thing. The real environment was a completely different nightmare. The tidal currents here reverse direction 4 times a day, pushing 400 million cubic meters of water. The giant mattresses had to be placed perfectly flat on the dark seabed, fighting these extreme ocean forces. One fold, one tear in the fabric, and the 18,000-ton pillar above it will eventually collapse. To lay these mattresses perfectly flat, engineers had to invent a machine that had never existed. They called it the cardium. It was a highly specialized, bizarre-looking vessel. It featured a massive rotating cylinder capable of holding a 200-meter fabric roll. On land, the gigantic rock-filled mattress was slowly wound onto this steel cylinder, exactly like rolling up a massive, heavy carpet. Cardium then sailed out into the violent estuary. Once in position, the heavy cylinder was lowered deep into the turbulent water. Acoustic underwater sensors and early GPS technology guided the ship. They achieved a placement accuracy of less than 5 centimeters. Exactly 65 times they repeated this dangerous process in the dark. Finally, the liquid seabed was locked. The quicksand was conquered. With the foundation secure, they faced the next impossible task. How do you move an 18,000-ton concrete pillar into the ocean? You cannot lift it with standard cranes. So, they flooded the massive construction dry dock, letting the ocean rush in. Because the concrete pillars were completely hollow inside, they actually floated, like gigantic, heavy rectangular ships made of solid stone. But they needed a way to control them. Enter the Ostrea, a custom-built U-shaped lifting vessel the size of a football stadium. With the pillar securely clamped, a fleet of tugboats dragged the colossal assembly out into the freezing, chaotic North Sea. The journey was extremely treacherous. One heavy wave could snap the towing cables, sending the cathedral of concrete crashing to the bottom. They successfully reached the drop zone, but the tidal weather window to safely lower 18,000 tons was exactly 60 minutes. The tide completely stops. Slack water. They have just 60 minutes to lower 18,000 tons through 45 meters of water. Using early acoustic tracking technology, operators guided the massive block down in total darkness. The margin of error was terrifying. It touched down flawlessly. They repeated this nerve-wracking process exactly 65 times. The skeleton of the barrier was finally in place. To ensure they never moved, specialized ships dumped 5 million tons of heavy rock directly around their bases, locking them permanently. Now they had to build the mechanical muscles, the massive steel gates that would actually block the North Sea. The welds had to be flawless. X-ray inspections checked every single millimeter of the joints for microscopic fractures. A completely different fleet of heavy-lift crane ships transported the freshly painted gates out to the pillars in the ocean. The gates had to slide flawlessly into narrow concrete grooves on the sides of the pillars, like assembling a giant watch. To move these massive gates, they installed the largest hydraulic cylinders ever built. Each one pushes with the force of a rocket engine. They operate on a pure gravity failsafe. If the power grid completely fails during a hurricane, gravity naturally drops the gates shut. The entire network is controlled by a central brain, a highly automated computer system continuously analyzing weather and incoming tidal data. Under normal conditions, the gates stay open. The tides flow freely, keeping the delicate saltwater ecosystem completely alive and thriving. But installing the massive steel arms revealed a terrifying problem. 1 millimeter of error here, and the entire gate would jam permanently. To prevent the metal from grinding, they engineered specialized synthetic polymer bearings, designed to last 200 years without lubrication. Workers installed these custom pads inside the narrow concrete grooves. It allowed the 500-ton gates to slide with zero friction. In 1886, the Eastern Scheldt Barrier was finally declared operational, a 9-kilometer shield of raw concrete and steel. But the Delta Works was not finished. Remember the busiest port in Europe? Rotterdam was still completely exposed to the sea. They could not build pillars here. The massive shipping channel had to remain completely open, 365 days a year. The solution was the Maeslantkering, a storm surge barrier so radically different it looked like something out of a science fiction movie. Each of these hollow steel arms is exactly the same length as the Eiffel Tower, laying horizontally on the open water. Constructing them required forging thousands of tons of high-grade steel, the exact same material used for building deep-sea military submarines. To swing these massive structures against ocean currents, they had to invent the largest ball and socket joints in human history. Each spherical steel joint is 10 meters in diameter. It weighs an incredible 680 tons. A surface flaw the size of a human hair would cause catastrophic structural failure during a hurricane. The Eiffel Tower-sized arms were then welded directly to these spheres, creating a flawless mechanical pivot point capable of unimaginable force. But swinging floating steel is not enough to stop a storm surge. To actually block the ocean, the floating arms have to sink. The solution is brilliantly simple. The steel arms are completely hollow inside. When the order is given, massive internal valves open wide. Millions of gallons of river water rush directly into the steel chambers. The enormous weight forces the floating arms to sink. They do not just sink randomly. They descend perfectly onto a specialized concrete bed sitting deep at the bottom of the channel. The water pressure from the storm surge actually pushes the sunken arms down even harder, locking them perfectly against the riverbed. Engineers installed gigantic rubber gaskets. The massive hydrostatic pressure crushes the rubber, creating an absolutely watertight seal across. Filled with air again, the 6,000-ton arms float back up to the surface and quietly swing back into their dry docks. Within hours, the massive container ships of Rotterdam continue their journeys. The economic heart of Europe never stops beating. But the most terrifying part of this barrier? It has no human operators. A central supercomputer makes every single decision. The computer constantly calculates tidal data and storm predictions. If it calculates a surge over 3 meters, it closes the gates automatically. In 1987, the final piece was completed. The Delta Works, a project that took 4 years, was officially finished. It moved millions of tons of stone, poured endless concrete, forged steel giants, all to mathematically shorten their vulnerable coastline. The nation was finally safe behind an impenetrable fortress. The trauma of 1953 would never happen again. The ocean does not negotiate. In 2007, a violent superstorm forced the entire system to its absolute limits. November 2007, Cyclone Tylo slams into the North Sea, pushing a massive 3-meter storm surge toward Rotterdam. Surge detected. Auto closure initiated. For the first time in history, all major barriers of the Delta Works shut completely. The nation braces for impact. Millions of tons of seawater slam into the steel gates. The hydrostatic pressure tests every weld, every joint. Deep underwater, the ocean currents violently try to wash the seabed away. But the high-tech foundation mattresses hold perfectly. The next morning, the sun rises over a completely dry nation. The Delta Works held. Not a single drop breached the defenses. It is a flawless masterpiece of engineering. But engineers know a terrifying truth about fighting the ocean. The Delta Works was designed for a 1 in 10,000 year storm. But global sea levels are rising faster than originally predicted. In the coming decades, these monumental walls might not be high enough. They may have to rebuild the entire system again. Now, it stands as one of the 7 wonders of the modern world. A masterpiece of human survival. Every single metre of this 29,000-kilometer shield was paid for in billions of dollars and decades of relentless labor. It is finished. It has been tested. It held perfectly. But the massive North Sea does not negotiate. The ultimate question is not whether this megastructure will be tested again. The question is only, when? If you want to see how Japan built a 400-kilometer tsunami wall after their disaster, click the video on screen. Subscribe for more deep dives into the mega projects that are quietly shaping our world. Goodbye.